And we are back, and we are going to get into our, excuse the noise, into our Pset 6 solution video. So let's go ahead and get started. So we're looking at a ceramic material. So I know my Young's modulus is 300 gigapascals, stress strain curve below. Consider the following scenario of two dislocations described below. So let's go ahead and we'll pull out our handy dandy notebook. And if you remember, we have, and we'll leave it in kind of these general forms. We're not going to evaluate it. But we have our expression for if we have basically our edge stress, and then we have similarly our screw stress actually right here. But we actually need to make an adjustment here because as we saw in class, and remember, these are for very, very, very specific basically types of dislocations. So we only know it when for the screw, or actually for the edge, excuse me, when our tangent direction is in the positive 3 direction, and then when our Burgers vector is in the positive 1 direction, effectively. And additionally, we know for basically for our screw, XY, actually should be XZ. I'm going to change that right now. XZ, XCS, and then XYZ here and here. And for our screw stress, again, it's going to be sig XZS, sig XZS, and then we'll get those values here in just a second here. There is no sig there. There is going to be one in the 1,3 here, and then the YZS, and then we need right here, YZ here. There we go. So that's our screw stress. So screw stress, edge stress, now we can start to kind of move forward here. So if we want our PK, so let's go ahead and let's kind of continue to work in here. So I'm going to say T1 is equal to 0, 0, 1. My B1 is equal to 0, 0, minus 1. I know that my B2 is equal to minus 1, 0, 0. And our tangent, our T2, is still going to be in the 0, 0, 1 direction. So obviously, my first dislocation is a what? It's actually a left screw. And what about my edge dislocation? Or which is actually R2 is going to be an edge dislocation. Look, sorry, ruined the moment there. But the first dislocation is a left-handed screw because they're anti-parallel. Excellent. So what is the force of dislocation 1 on 2? So remember, we're going to have to take, so 1 on 2 would be basically screw, actually we'd have to do cross of screw stress, dot, and then, so 1 on 2. So we'd have to do B2 cross T2. And remember, that is from our, what type of force? What are we calculating here? This is our PK force. So dot B2 cross that. And so what can we see here? There's not going to be any force in any direction. So remember, force is a vector. It's a first rank tensor property. What about 2 on 1? So that'd be edge stress on B1, T1. And what do we get? Nothing as well. So that was quick there. So what is the resolved shear stress of 1 on 2 and be quantitative? Well, we can kind of, actually, so 1 on 2. So what is my normal, or what is, again, if we look at our, actually we have our shear stress there. So how can we calculate our resolved shear stress? So we have some stress tensor that is going to be my, from 1, which we've decided, which is our screw stress right here. So that's our screw stress. And then we can kind of see where that is going to be applied on our plane of interest, which is going to be our B2, T2. So I could actually do this, my normal of my edge, or actually screw dislocation, or not screws, it's actually, it's a basically just an edge dislocation. So let's go ahead and do T1. Actually 1 on 2, excuse me. So actually T2, T2, B2, T2, B2. So that's our normal. We can take our B2, B2 function here, and we can do alpha ij times our, we can just plug in essentially that screw stress, and 0. So again, nothing super exciting here, as we may have anticipated. So nothing's going on here. But let's say I remove dislocation 1, so forget about that, and apply the following stress state on my material. So let's just do a sig gen equals, so 31, 0, minus 17. So let me get this here. 0, comma, minus 17. Then I'm going to go here. I'm going to go 0, 88, 65, and then finally I'm going to go minus 17, 65, 41. And these are all in MPa. So that's my SIGGEN. So I could actually, instead of looking at this value here, I can go to here to calculate my resolve. What was the resolve just here? Now I apply this following stress on material. What is my resolved shear stress? So I can do SIGGEN, and that's also 0. So what is the large dislocation that we can basically work with here? It's nothing. So again, we could actually revisit this, but exactly 1 on 2. So we still have our B2 here, T2 here. And again, technically, we really even couldn't do the edge stress here, but that's a little bit of a another essentially problem with this problem. But again, if we have this flatten it alpha ij, even if we have our new edge here, T2 B2, and nothing. So 0, 0, 0, and that's what we got. Assuming lattice resistant critical yield stress, can we move dislocations via dislocation glide, or will thermal energy be required here? So again, because there is effectively no correct, or basically we don't have any resolved shear stress, then we really can't even answer that question. So actually, lattice equivalent to the yield stress, can we move dislocations via dislocation glide, or will thermal energy be required? Well, so lattice resistance is equal to this, but because we have no resolved shear stress, we're definitely going to need thermal energy in order to answer that question. Answer the same questions C and D, but now I remove dislocation 2 and apply the same stress state. So let's do C and D now. So what happens if we, so let's read that problem one more time. But now I remove dislocation 2. So now instead of, so let's look at trying to solve this. Yeah. So let's go ahead and do this now. But we all know what's going to happen here. What happens if we do T1, B1? Is there a glide plane for a screw? No. So that's it. Unfortunately, we don't get any solution essentially for this particular problem. So again, it's a bit of a null problem, but kind of walks you through essentially the process and how you would work for it. All right, now I'm working with vanadium and have the following defect reaction. Actually, what is vanadium? So let's look at periodic table. Let's look at what is vanadium. I believe it is BCC, but let's double check it. So we see the cross there. Yep, cubic body centered. So it is a BCC system. So we know, and if we're looking at defects and defect reactions, for BCC, what is my slip system? So close packed directions, 1, 1, 1. Close packed planes, or closest packed planes would be 1, 1, 0. So those are the mobile dislocations. So I'm working with following defect reactions just so that the two reactant vectors here. So let's go ahead and work with these defect reactions. So I'm just going to move this over here. So I'm going to do result equals basically A divided by 6 times 1, or actually 0, 1, 1 plus a over 6, let's do a divided by 6, times, actually plus 0, 1, 1. So this is our resultant vector, as we see here, and you can factor that out, a over 3, and we can work with that. Now we need to see if the reaction is spontaneous. So we can do that by basically invoking Frank's rule, which is essentially saying that we need the sum of the squares of the reactant basically defects must be smaller than the sum of the squares of the resultant defects. So remember, we don't want to create larger defects in our system. So if we compare the sum of the squares of the Burgers vector of the reactants to that of the products, we should be able to see if it's spontaneous or not, and they need to be less. So I'm just going to take norm of my result, and I'm going to square that, and then we're going to ask, is this larger than this plus the exact same? So let's see what we got. So which is larger? So let's see, is this greater than this? Actually, we can ask. So is our result greater than this? Well, assuming that A is larger. Yep. So that's not good. So it is not going to be a spontaneous reaction. What is the slip system of the resultant dislocation? Is it motile or sessile? So we actually already determined the slip system, but we actually have to kind of figure that out now. So we know our Burgers vector is just our resultant vector here. So that's already what? If you factor out a over 3, 0, 1, 1. So 0, 1, 1 is not a, basically it's not a direction that is, I mean, it's not a direction, it is not a close packed direction. So it is not a motile direction. So that's already not good. But we need to also figure out what is our tangent. And our tangent is simply going to be basically taking the normal of each of these planes, crossing it, and figuring out where that lies, just like we've done in class previously. 1, 1, 0. And we can take this, we can put them here, and here's our T result. And we know our B result is equal to, let's just call it result. And let's cross. And again, I want to figure out now the plane. So this is my resultant Burgers vector, my tangent vector here. We know our equation to get the normal to the plane once we have a tangent and Burgers vector. And let's see what we got. And if we factor these out, what do we have? So it is a 0, basically 1 minus 1 plane. So we are actually in the kind of closest packed directions, but we are not. So this is not a slip system. Excellent. All right, I have a following defect pairs described below, and then, actually, it's very similar to the ones that we, actually, similar, but not the same, actually. Not the same at all. So I have the following defect pairs described below, so actually, let's go back and let's work with these again. So I'm going to, I'm going to just reevaluate this. 0, 1, 0, and I want to do 0, 0, 1. Then Burgers 0, 0, 1, and then this is 0, 0, minus 1. I just want to double check this. 0, 1, 0, boom, boom. So we know that 1 is what? So 1 again is going to be an edge dislocation. 2 is going to be a left-hand screw once again. So for each of the defect, describe whether vacancies or interstitials will want to form at these locations. So let's go ahead and take a peek at this. So, oops. All right. For each of these, so will they want to form? So we know, again, when we're looking at basically interactions with point defects, we had an expression that effectively described how the interactions are going to, or basically, how defects and how dislocations will interact with point defects. And it had to do with essentially this expression of delta H formation, new, same delta H formation of some, again, you could probably put it on the top here. That's what I'm doing right now. Formation of, vacancy, some H of an interstitial, a vacancy, plus our basically P delta V, and then basically a change in atomic volume, let me move this over, of, a vacancy, for example. So this could be a vacancy, or this could be an interstitial as well. So we previously essentially described, and we said that the change, if I'm looking at an interstitial versus a vacancy, so what is my change in volume? So for an interstitial, my change in volume of the surrounding atom is going to be positive. My change in volume of a vacancy is actually going to be negative. We also know that our pressure is equal to minus 1/3 of the trace of our stress tensor. So, which is going to be basically our normal stresses. So when we are when our stress is in tension, so plus, so when our pressure, we can just say that here. So when our stress is in tension, that leads to our pressure being negative. When our stress is compressive, our pressure is positive. And you can kind of see how that effectively works out as well. So with that knowledge and knowing that this is a screw defect, we know, for example, and it's going to be the stress fields interacting with it, we know that our screw stress, glad I didn't finish that, there are no pressure defects, or pressure, there are no hydrostatic pressure stress components. So our diagonal is always 0 based, from the screw defect. So these will have no interactions whatsoever. Now, here, for my, edge dislocation, or edge defect, I am going to have, in this location, my stress is going to be very negative. It's compressed. Whereas here, our stress is going to be positive. So, if I'm looking at, in this location here, so if I'm looking at where, let's say, for example, I'm going to call this top, and I'm going to call this bottom. So, top, bottom, and this is going to hold for, so what's going to happen here? If I'm an interstitial at the top, right? Actually, we'll see, we'll write form or not form. So if I'm an interstitial and I'm looking at the top here, that is a compressive stress. So that means that the pressure is what? Pressure is positive. So positive here. As I change my interstitial, that's positive. So I'm increasing the energy, so they will not form here. If I'm looking here at the bottom, so now my stress is positive, my pressure is negative, so this term now becomes negative, it's reducing it, so interstitials will want to form at the bottom of that defect, so they will form. For vacancies, it's the exact opposite, right? So if I'm looking at negative compression, that's positive here, positive pressure, but my change in volume is negative for my vacancy, so they will form here, but they will not form here because remember, positive here, so that's a negative pressure, negative change in volume, positive, I'm increasing the energy of formation, not going to happen. Excellent. For any arbitrary applied stress state, will stresses contribute to glide? For each which stresses will contribute to glide, which will result in climb? We can do that for this one, because we know, for example, if I look at cross, and I'm just going to do, there should be a siggen here, or do I just have a, I'm looking for just a generic stress tensor. Here we go, sig. So if I look at essentially which stresses will contribute to glide, so first of all, I need to figure out, let's first just essentially, there's not really going to be glide for the for the screw stresses, but let's look at what forces will essentially move those defects. That's a better way to kind of to frame that problem. So if I do cross sig, and I know that my B2 and T2 are my, I do know those. Actually, I do know it for all of those two. And I'll do sig. So here we go. So if I'm looking at, basically looking at, if I'm in the glide plane, or if I'm looking at those, basically I could look at, actually, which just was in climb. So actually basically in the opposite direction. So if we are in, actually this location, so if we're moving essentially within the plane, or our glide plane, and actually we can do that by looking at, so we could actually deduce our glide plane as such. So we know that there's no glide plane here, but these would be the forces that would be acting on this. But for T1, and for B1, and for T1, and then for B1. So our glide plane would be basically in that 1, 0, 0 plane. So this would be essentially, if we're, kind of projecting or looking essentially at motion, along or essentially in that direction, it would be, in that 1, 0, 0 plane. If you're moving along, if you kind of imagine that your defect is at the origin, this is going to move basically in that 1, 0, 0 direction, or in that 1, 0, 0 plane, and then hence in that direction. This will be kind of perpendicular to it, so that would be essentially your climb component. So good little problem there. Excellent. Calculate the PK force, glide planes, and resolve shear stresses for the following scenarios. Ooh, excellent. All right, so let's go ahead and take a peek at this. So edge dislocation on edge dislocation both have tangent vectors aligned with Z, and Burger's vector aligned in the X direction. Edge on edge. So let's go ahead. So actually we can do that. We can calculate those. So we want our T1 edge on edge. So again, I'm just going to call it the second one there. Our T1 is this direction here. So this would be my glide. So this is my glide plane. If I want to look at the PK forces, it is going to be, again, edge dislocation on edge dislocation. So, and they both have that. So edge stress. So on, excuse me, do B1, T1. So those would be essentially my PK force. What would be the resolved shear stress? So let's go ahead and let's do the norm here. And not the B2. We fix that from B1, B1. So the normal there. And then I'm looking at alpha ij times edge stress. And then voila. So that would essentially be the resolved shear stress there. Edge dislocation on left screw. So the PK force of that on that, the edge dislocation has a tangent vector in the Z, Burger's vector in the X, while the screw has a tangent vector. So let's go ahead and just copy those. Screw has a tangent vector aligned, or the left screw has a tangent vector aligned in the Z. So if it's left, it must be -1 here, 0. There will be no glide plane, as we know. So no glide plane. We can look at the edge stress, edge on this. So it'd be nothing there. And I'd imagine we can't do the rest because there's no normal. Yeah, excellent. Right hand screw and right hand screw. So again, no glide plane, no resolved shear stress. What about the PK force? So the PK force will simply be, let's see, right hand screw on right hand screw. The right hand screw has a tangent vector in the Z direction. And the left hand screw has a tangent vector in the positive Z direction. I think that is a little bit of an error. So we're just going to go tangent here. It's a tangent vector in the Z direction, so it needs to be aligned. So we know that, we know that. This will be screw stress. So we'd have those PK forces, but that is unfortunately all that we've got. And then a right hand screw on an edge dislocation. Right hand screw is a positive tangent vector in the Z direction, and the edge is a tangent vector in the positive Z direction, and the Burger's vector in the positive X direction. So right hand screw on, so we need this, we need this, we have this, 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 right hand screw, we're good there, so we still have our screw stress, and then voila, nothing there. We do have a normal direction, T1, B1 here, so we can do that, and then we can do, this is edge stress, again this has to be screw stress, and 0. That's it. So again, just make sure you kind of walk through those. Again, a lot of these were null values, but they're kind of intentional to kind of show you essentially how you want to approach these problems, and then that's it. Good luck on Pset 6, and we'll see you all next time. Thanks. Bye.